Welcome to Homework Lib.
So in this question, we want to find the wavelength of the photon emitted when the molecule sodium chloride goes from energy level 2 to energy level 1, and then again to energy level 0. But in this case, we have two isotopes of chloride. We have chloride 35 and chloride 37, and they have different masses. So that changes the total reduced mass of this molecule, which further changes the moment of inertia and the amount of energy. And we need to calculate the energy for both types of isotopes. Let's first start with sodium chloride 35. So chloride 35. So the reduced mass is sodium and of chloride, mass of sodium plus mass of chloride. This is equal to 3.82 times 10 to the negative 26 kilograms. This is the mass of the sodium. You can use more significant digits if you like. I'm going to use 3. This is equal to 2.3 times 10 to the negative 26 kilograms. This is a reduced mass of this molecule. And then, knowing that, we will be able to find the moment of inertia. The moment of inertia is reduced mass times the distance between the two atoms squared. So 2.3 times the distance was given to us from the question. Equals 1.28 times 10 to the negative 45 kilogram per meter squared. So this is a moment of inertia. So finally, let's look at the wavelength emitted when it transits from L equals 2 to L equals 1, and then when it transits from L equals 1 to L equals 0. So when it goes from L equals 2 to L equals 1, let me think about what is the most efficient way of saying it. It might be easier if we first calculate the energy. Delta energy of 2 equals 1 is E2 minus E1 equals 6 minus 2, because 2 times 3 minus 1 times 2 times h bar square over 2I. And so this is just equal to 2 h bar square over 2I, which is 2 times 1.05 times 10 to the negative 34 joule per second squared over 1.28 times 10 to the negative 45 kilogram times meter squared. And together, this is equal to 1.734 times 10 to the negative 23 joule. Okay, let me try to move everything up a little bit so we have more space. Right. Let's try to continue. 23 joule. And then the next step is, if we already know what the energy is, we need to find the wavelength corresponding to this energy. So the wavelength can be found by the energy equals hc over lambda. So the wavelength lambda is equal to hc over delta E, and delta E we found in the previous section. So this is equal to 6.626 times 10 to the negative 34 joule per second times 3 times 10 to the 8th meter per second over 1.734 times 10 to the negative 23 joule, as we found in the previous equation. This gives us a wavelength of 1.146 times 10 to the negative 2 meter, which is roughly 1.15 centimeter. So this is the wavelength of the light that will be emitted when we go from energy level L equals 2 to L equals 1. And we can find the transition from L equals 1 to L equals 0 with the same exact same procedure. So I will not write down all the equations again, but let me just say this is when we go from, this is sodium chloride 35 from 2 to 1. When we go from 1 to 0, what differs is that now the energy is E1 minus E0, which is h bar squared over I. So this is roughly half the energy of the previous case. So the new energy is 8.67 times 10 to the negative 24 joule. And the wavelength lambda is going to be lambda equals 2.291 centimeter. So the lambda is actually, you see the energy is half, so the wavelength is twice the previous case. All right, so these are the two results we had for sodium chloride 35. What about sodium chloride 37? For sodium chloride 37, what is changing is that for this number, instead of 5.81, we will be using 6.14. So if you sort of redo this process, but with the new mass equals 6.14, then you will find this new reduced mass of 2.35. So that's a lesson that I should have used more significant digits over here. Previously it was 2.30, now it becomes 2.35. So if you use 2.35 as a new mass, and then the new moment of inertia you get will be 1.312. And similarly, when you find the following questions, the energy you get will be 1.697 times 10 to the negative 23, and the wavelength you get will be 1.171 centimeter. So we can see that when the mass gets larger, the amount of energy actually gets smaller, so the wavelength gets longer. So M37 chloride. And then if you find L equals 2 to L equals 1, what you'll find is that the energy from 1 to 0 is 8.485 times 10 to the negative 24 joule. Again, it's half of the previous section when it goes from 1 to 0, and the lambda, corresponding lambda, is 2.34. 2.341 centimeter. And as well, it's pretty much it's pretty much twice the previous wavelength. So that is this question. It's a little bit messy. We really have 8 results in these 4 equations that I'm using, but I hope you follows, and All the blue results are the corresponding numbers for 37 chloride, and the black result are black and green are for 35 chloride.